the single most important concept to understand when using data to manage a system is variation. Now, all systems have noise within them. It's what we call common cause variation or routine variation. But every now and then there will be a stronger signal, what we call special cause, a single dominant event that has caused the system to change. You've probably heard of common and special cause before, but I'm just going to go over and explain it one more time just to make sure that we've got this critical concept. I'm going to start off with an example. Let's imagine that you are an archer and you're firing arrows at the target which is 70 meters away. Not all of your targets hit the bullseye. Why not? Well, there's variation in the way that you pull back the string in the bow or let go, or maybe there's different gusts of wind, or maybe there's differences in the arrows. There are slight differences in the weight or the flex of the arrows. There's lots of different things that add up to variation, what we call common cause variation. But you can see that one of the arrows missed the target completely. Now, this is what we call special cause variation, and it's usually one single dominant event that created this. It could have been a bird that fluttered in your face just as you were about to shoot. Or maybe somebody bumped into you just as you were about to let go of the string and fire the arrow towards the target. Whatever it is, you have to find and fix that special cause, because otherwise you'll never be a good archer. So it's really important that we're able to determine between the system noise, the common cause variation, the routine stuff, and those special signals that tell us that the system has actually changed. Now, I'm sure you've all come across this concept of common cause and special cause variation. But I just want to make sure that we've got this absolutely nailed, because it's really, really important. So I'm going to go through another example. I'm going to think about your commute time to work. Now, this is probably pre-COVID, because it would take you about 10 seconds to get into your home office nowadays when you're working from home. But think about your normal commute pre-COVID. And the key thing is, it didn't take you the same length of time each day. There was variation in your system. So why is that? Well, if you think about the process, and the example I'm going to use is driving to work, because that's what I was doing when I first came across this concept. So if I think about my drive time to work, it was variable because sometimes I caught the traffic lights at green, next time they were at red, or I got stuck behind a cyclist or maybe a tractor, or I happened to get a clear piece of road and managed to get in a little bit quicker. The weather makes quite a difference to the commute time. If it's dark and rainy, people tend to drive a little bit slower compared to a bright, clear, sunny day where they'd speed up a bit and you get into work that little bit faster. So what about potentially some special cause reasons that might slow you down? Well, you might have a puncture. That would slow you down. Or there's an accident. Or there's some bad weather that slows you down. And what about special cause reasons that might speed you up? Well, there could be the COVID crisis. When there's nobody on the road, obviously it would be much quicker to get into work. So do you think we've got this concept of the difference between common and special cause? I don't know whether you noticed, but I listed weather as both a common cause and a special cause. So how are we making this differentiation? How do we tell whether weather is a common cause or whether is a special cause? Now, I hope you said that you would differentiate between common and special cause using data, because after all, this is a data class. So I'm going to look at some data that I collected when I first came across this concept many years ago. And I was driving to work, as I said, and every time I got into work, I would write down the time it took me on a little post-it note. And I used these post-it notes to build up a distribution, a snapshot of my journey into work. And you can see that there was no instances where I made it into work in less than 17 minutes, and no instances where it was more than 43 minutes. But there was considerable variation in between. So in the category 17 to 20 minutes, there were 2 instances when that happened. And then 7 between 21 and 24, and 12 between 25 and 28 minutes, and so on. Okay? The average was just above 25 minutes. But I couldn't use that to judge when to leave work, to leave home to get to work in time. I had to use the upper limit of 43 minutes. So if I left 43 minutes ahead of time, then I was probably going to get to work on time, as long as there was only common cause variation. The key thing is, if there's something outside of this distribution, on either side of it, that's a signal that the system has changed. So for example, in terms of bad weather, if it's dark and rainy and cold, and it slows my journey down and it takes 37 minutes, that's inside the distribution, and therefore we classify that as common cause. If it's snowy and it takes me an hour and a half, that is clearly outside the distribution, and it's special cause. But it's important that we use the data because sometimes it's close to the limits. So if it's a bad weather day that takes me, for example, 42 minutes, that's still common cause variation, and we can't say that our system has changed. The key point here is that we need to use data to differentiate between common and special cause. And one way of doing that is to build up a distribution or a bell-shaped curve, as you can see on the bottom of this slide. And everything that's inside the bell-shaped curve we determine as common cause variation. Everything that's outside is special cause. So if it's common cause, then we know that those limits are the best that we can do. In my example of driving to work, I knew it was between 17 and 43 minutes. So it's quite variable, but it's consistent. And as long as I know that and I can plan for that, I can predict what's going to happen in the short to medium term. Now, if you want to improve that particular process, you would need to assemble a project team and study the process in detail. However, in the case of the heavy snow or an accident, then that clearly belongs to a different data set because it's outside the distribution. And we call that special cause variation. And we need to find that and fix it, because otherwise we don't know what's going to happen next time, because our process is unstable and unpredictable. So here is an example of a control chart, which is the single best way of detecting special cause or system change. It's simply the data plotted with respect to time, and then we add limits. The two red lines are upper control limit and a lower control limit. And we know that any points outside of those limits are a strong signal for system change. And we need to go and investigate that, potentially find that and fix it. Not many people realise the link between the control chart and the distribution that we looked at earlier. It's pretty simple. Let's take an example. Let's say you've got a control chart with some data in it. What you're going to do is take that, which is lying horizontally at the moment, and turn it vertically. And then once it's vertical, you're going to remove the time element and collapse all of the points onto the baseline. And when you do that, you'll find that the points add up together to form a distribution. In this case, it's a nice bell-shaped distribution, but it doesn't always have to be like that. And the interesting thing is we know that anything inside the distribution, common cause variation, anything outside the distribution is special cause variation. And the limits on the control chart are the same as the limits on the distribution. And that is the link. Now, it's critical that we're able to differentiate between common cause and special cause variation. And the best way of doing that is using the control chart. However, the distribution can also be very helpful because it gives us a snapshot of our system, and then anything outside the distribution is special cause, and anything inside the distribution is common cause variation.